We'll wait for the last papers to put those down. Let me go through the curve. Let me just go through the exam quickly before we go through it. Again, the mean was in the 53-ish range. Mean was around 53. The high was a 93. The low was a 13. In general, there was a nice distribution, which you see here. And again, I will curve at the end. The exact value of what the mean is unimportant, okay? What matters, I think, is whether you are, the only people I'm worried about are the ones that are really well below the mean, okay? So, the people who I'm most worried about are in the range about here, okay? And, in the low 30s on down, okay? And, in general, the grades here correlated extremely well with the first midterm. There were a few people who made big jumps after the first midterm, but in general, they were fairly well correlated with that. Any questions before I get started going over it? Yes. The answer is after class. After class, we'll pass out the midterms again, just because we're already a little bit late. Okay, let me go through what the problems were and how this was graded. And again, if there are grading mistakes, I want to know about it. A grading mistake is defined as one where you got the right answer and we marked it wrong, okay? A grading mistake is not one where we took off more points than you think we should have for a wrong answer, okay? I want to make clear that that's my position on here. Okay, problem number 1. I think it's fairly straightforward. It was about executing various graph algorithms, basic graph algorithms on different graphs. And again, I could go through and read out. How many people want me to read out answers? Okay, here are a couple people. How many people don't want me to read out answers for this one? It's not as big as a win as I wanted. Okay, how do you do it for a breadth first search? You should start in the upper diagonal and scan across diagonally. That's basically what it means to radiate out in this case. So it's A, B, E, C, F, I, D, G, J, H, M, H, K, N, L, O, P. Depth first search. It's more like following a snake order around this thing. So it's A, B, C, D, H, G, F, E, I, J, K, L, P, O, M, N, M. For the shortest path minimum spanning tree, it looks sort of like a U with the top right part of the U taken out. Okay, zoop, that's what it is. For the shortest path spanning tree, again, it starts at the left corner and radiates out. Any questions there? It's hard to read that one out loud. Okay, any questions? Okay, so that was about executing algorithms. Now for the second problem was the backtracking problem. The backtracking problem says that you are given a prime factorization of an integer, and it says to construct the complete set of its divisors. Okay? So one way you could do it, if you wanted to get the wrong answer, would have been to multiply the prime factors together and now repeatedly try every possible divisor from 1 to n. Okay? That is very expensive. Okay? The number of divisors is typically logarithmic in the number of integers. So if you just do it by trial division, that is bad, and I said you had to use backtracking. Some people said any possible, any possible divisor is represented by a subset of its prime factorization. So they said, I will list all the subsets, and I will list all the subsets of all the possible factors. And that's not completely wrong, but what is a problem? If you have identical factors, let's say you take 16. 16 is 2 times 2 times 2 times 2, okay? Or in general, 2 to the n. There are 2 to the n subsets of n different 2's. That would argue that you have to try all 2 to the n of them. You're going to have the same divisor many, many times. Does everybody see that if you just try all possible subsets of the divisors raw, okay, you will end up getting the same divisor many times, okay? And that is not efficient, okay? Any questions? What is the way that I would have represented it? I would have represented my solution space if there are k different unique prime factors, okay? In the 2 examples, like 72 has 2 unique prime factors, 2 and 3. What I would have done is I would have had k, okay, slots in my solution vector. And for each prime factor, I'm allowed to have somewhere between 0 and the number of times that prime factor occurred, okay, occurrences of that factor in my divisor, okay? And then what I would be doing is the value, do people see what I mean by that? Let me just make sure that's clear. Okay, so let's consider a number like 72. 72 is made of 2's and 3's. There are 3 possible 2's, okay, and 2 3's that when all multiplied together made 72. Does everybody agree with that? My solution vector would have been to have 2 slots, and this value has a number. This slot has a value between 0 and 3, and this one has a value of between 0 and 2. Okay, and that's the number of times I can have 2's. There's a number of times I can have 3's, and I now construct all solutions which have a permissible number of occurrences. Yes?
So to check if a candidate is a solution, you can see that all those counts are between 0 and maximum subfactor.
Okay, what?
So a candidate is a solution if the count of each factor is between 0.
Okay, so what would I do now? How would I organize this? Okay, now how do I break this down? Okay, so where would I divide my work up? My candidates. What are the candidates for the ith position? It's the numbers between 0 and the multiplicity of the ith number. Okay? So whenever I'm filling something in, suppose let's say I'd already filled in a 0 here. What are the choices for this value? It would have been the numbers 0, 1, and 2. Okay? That's what my construct candidates would have been. When do I have a solution? I have a solution when I filled in all values of my array with something that's with values. So when n equals k, a similar condition when I filled up that thing. And then what would my process solution be? Well, I probably want to fill out the, I probably want to multiply out and compute what the divisor is. And if so, I might as well convert that from this prime factor representation back to the other by multiplying. Okay? That's what my solution would have been. Any questions about that? Okay? And again, the problem is you want to avoid overcounting, which is what you got some credit for saying, give me all subsets, but I think the most common mistake was that you would overcount if you did that. Any questions about this one? Okay, good. Item number 3 was on modifying edit distance, okay, to the case where you also are allowed to have a swap operation, where your fingers hit the keys in the wrong order, okay? And if that's true, then we would still count that as one edit correction mistake. So what would I do here? Again, the first question was, how do you go about modifying the recurrence relation? Well, again, what is it? Dij is going to be the min number of changes from string s from 1 to I to string t from 1 to j. That's the definition of what we're trying to compute. What is the recurrence relation? Seems to me that Dij is going to be the same as it was before, except we have allowed another option. So what is it min going to be? We could end on an insert, in which case it would be 1 plus d of I minus 1, j minus 1. We could end on a delete, in which case it would be 1 plus that. We could end on a substitution, in which case it was I minus 1, j minus 1, plus the match question. True or false does, what is the cost of editing? S sub I into T of j. Right? If they were the same character, this would be 0. If it was different, it would be 1. Plus, we now need to add the other case, which is the swap. What is the key issue with the swap? Okay? First thing is to note that in a swap, the history goes back 2 in both dimensions. So it's I minus 2, j minus 2. Okay? Plus, we also have to make sure the characters are good. We're allowed to do this plus a cost of 1 if the characters are allowable on the swap, which basically means a condition like S sub I is equal to T of j minus 1. Okay? And S sub I minus 1 is equal to T of j. Does everybody see that you can swap the last two characters? If and only if the last character here equals the next to last character there, and the next to last character here equals the last character there. So this is the recurrence term. The history goes back if the characters allow it. Any questions about that? Then you got to fill out the matrix. I don't want to write the matrix out, but the cost here is that you can do this in a total of 2 swaps to convert apple to maple. Okay? Any questions? The AP and the LEEL. Okay? Any questions? Okay. The next one says you are given want to find the shortest path of an unweighted DAG. Okay? Well, do that in linear time. Well, a DAG is a directed acyclic graph is a graph. We said if we have an unweighted graph, the right way to find the shortest path is by breadth first search. So that basically I just want to see the words breadth first search. If you said, oh, I can do it with Dijkstra's algorithm, you're right, but it's less efficient, and so you lost some points for that. Now the second one asks, now you have a weighted graph, and a weighted DAG, and you want to find the shortest path from it. Again, weighted graph, you can say do it with Dijkstra's algorithm, but that's less efficient. You get some points for saying Dijkstra, but that's not order n plus m. Okay? So how do we do this? Okay? How do we find the shortest path in a DAG? Whenever you see a DAG, there's one thing you want to do instinctively. What do you instinctively want to do to any DAG? Topologically sort it. Now, once you have it topologically sorted, what is interesting about it? All the vertices, all the edges are neatly ordered on a line, and all the edges go from left to right. Okay? Now, let's think about the shortest path from this vertex, or some vertex, to this. Okay? The shortest path to this vertex, by definition, has to only go through vertices to the left of it. Why? Because it's a topologically sorted DAG, right? You can't have an edge go there and go backwards, right? There's no edge that's going to the right. Therefore, what is the shortest path to some vertex V? It is going to involve the shortest path to some predecessor of V plus the weight of that edge. The edges that go in here, okay, are all paths going from the starting vertex to this, by definition, okay, are going to be the shortest path to some vertex plus one last edge. So this gives us a dynamic programming-like strategy, okay? What is the basic idea here? The basic idea is that let's let C sub I is equal to the cost, the shortest path from our start vertex V, the path length from V to vertex I. What is this? Okay? C sub I is going to be the min over all edges, as you know, over all, if we think of all x, okay, such that there is an edge from x to I, okay, of what? The cost of getting to x plus the weight of the edge that goes from x to I. Okay, let's think about this for a moment. Okay, let's say first vertex here is V. What is the cost of getting to vertex V? 0. So we know that V sub, that C sub V is going to be equal to 0. In general, what's the cost of getting to vertex V? Let's call this I guess. What's the cost of getting to I? Well, it's the cost of getting to some vertex plus that last edge hop. Okay, and this is what it's saying for all ingoing edges to this vertex I. Okay, we want to minimize the cost of getting to that vertex plus the cost of that weight. Any questions? Why is this order n plus m? That's what it costs to do the topological sorting. And note that for every vertex, the number of edges we're going to consider is proportional to the degree of that vertex. Every edge is being used exactly once here. Okay? And that's why if we're doing this, it's not really a loop, a for loop here. It's a loop through the adjacency list for all edges that are going into vertex I. Any questions about that? Okay? That is the idea here. Any questions? The last question asked for finding the minimum bottleneck spanning tree of a graph, where the bottleneck is defined by the length of the longest edge. Here we want to have the shortest, longest edge as possible. We want to minimize the length of the longest single edge. Okay? I asked you to draw me a tree with that property, and some of you may have noticed this is the same thing as the minimum spanning tree. Okay? And in fact, I guess if you look at this problem, there's two ways of doing it that make sense. One is to say, well, why don't I consider all the edges from smallest to largest? I will keep adding them to my tree until the graph is connected. Okay? If the graph is not connected when I keep adding these small edges, then it's certainly, I don't have a big enough edge yet to really be my bottleneck. If I add edges from smallest to biggest, the last edge I add, where the thing becomes connected, is the bottleneck edge. This, I think, should be pretty clear. Okay, and so a basic problem of one by one sort the edges and insert the smallest edges and test if it's connected would be a correct answer. The other observation would be to say, wait a second, this happens to be, the algorithm not only does that, but it also happens to give me a minimum spanning tree. In fact, the minimum spanning tree of any graph satisfies this property. Okay? It's exactly what Kruskal's algorithm does. We didn't really talk about that here as much as I would have liked. But Kruskal's algorithm does that. But even if not, Prim's algorithm does it too. Okay? Because again, why is it that Prim's algorithm is going to do the same thing? You start with your Primy thing, okay, and you have a tree that you're growing out, okay? Suppose by contradiction, Prim's algorithm put in an edge that was heavier than it needed to be, okay? That's such that this edge was not a bottleneck edge. Is that so? Well, there must have been some other edge Prim didn't pick. Okay? Because Prim didn't pick it, this has to be less than or equal to that. Okay? If so, then this edge, this is not a minimum spanning tree, but then this wouldn't be the bottleneck edge either, because you could have deleted it and made it smaller. Okay? Any questions about that? Okay? So that was the other component there. Okay? Any questions? Any questions about what this means? Now, if you have a right answer and we marked it wrong, we want to see it. If we added up the numbers wrong, we want to know about it. If we gave you fewer points than you wanted to get, I'm sorry. Okay, but we don't want to see it. Okay? Is any question? You understand the distinction? Okay? So if you've got something on your paper that was misgraded, please write a note on it and get it back to me. But if it's not a question about right or wrong, then I don't want to see it now. Any questions about that? Okay? Again, don't worry about the absolute score. That means nothing to me. Okay? Because everything will be curved at the end. Okay? Any questions? If you did better relative to the curve than last time, that's great. Okay? And keep it up. If you had a plunge on this one, you got it. So some students did. Okay? This means that we got to catch up on this kind of material again, because this stuff you'll see it again on the final in a couple weeks. Any questions?
Final's everything, right?
Final is everything. Now, one good thing, as I start to get my act together for the lecture today, the final is everything. One good thing about everything is that you've seen most of my everything so far. Okay? We've got one subject left to go. We've only got 2 weeks to go. So, let me see. Is this what I want? No. Give me another second. I'm afraid. Let me just get my act together. And let me go and say, good. Okay, this will take me just a second, I'm afraid, to deal with. File, save as. Talk to me, desktop, save. Good. On. Okay, any other questions about the midterm before I get on to other things? Yes?
Quick question.
What is the running time for Kruskal's algorithm? So again, there are different ways of implementing Kruskal's algorithm, and there is a fastest way to implement it using fancy heaps. But what happened when on your paper?
Oh no, I wrote mn log n. I wasn't sure. I think that's like sorting n and then adding each one.
Well, mn log n is kind of m times n log n is. M times n log n.
Log n.
Wait. So so let's think what it is. If you listed it as m n log m, this is very slow, excessively slow. Okay? If you listed it as m log n, okay, that's a more respectable time. Okay?
If you do using union, what is the fastest?
Okay, the Kruskal. Okay, so again, I didn't talk about these details, and I believe that with the, again, it depends upon how fancy a data structure you end up using. If you use let me just think about this. I believe that it is let me just think for a second. I believe that it is m log n is the running time of it. Okay, when you use it with the proper, with the standard union find. Okay. Any questions? Yes.
M log n.
Okay, so there are m log what? M. Okay, so recognize that the reason why I get callous here between this and this is recognize that m is order n squared. If m is order n squared, then note that what's the difference between log of n squared and log of n? Log of n is just a factor of 2, so big O-Y's, they're the same to me. Okay? Any questions? Okay? Fair enough. Okay. Let's get on to, the last topic of, which we're going to cover this semester. Hold on, let me see if I can do this. Kabunk. I think this is the right way to do it. And, view full. screen. Come on, sorry about the delay. Okay. So what we're going to talk about here is, again, I teach this course a lot. There's ebbs and flows and of how people are interested and not interested. Certain subjects like dynamic programming, people don't like and they don't understand. NP-Completeness is something students do like and they don't understand. Okay, so I think I think this is a good. People usually find this stuff kind of interesting that we're about to talk about, and it's kind of a bit of a transition from what we've been doing. Almost all semester, we've been talking about how do you design a fast algorithm. And for the rest of the semester, we're not really going to worry about designing fast algorithms anymore. We're going to be worrying about how do you argue or how do you tell that a problem does not have a fast algorithm. And we did a little bit of that when we were talking about the sorting lower bound. But even there, this is quite a different kind of an idea. And it's really kind of. Well, let me again. I'll give you the standard, motivation for why we're going to care about it. But it really gets into an interesting, what is really, I think, one of the most interesting or amazing or powerful ideas in all of computer science. This whole idea of NP-completeness, and it's sort of motivated by the problem of what do we have to do when we don't find a fast algorithm. Okay. There are many problems in the world for which, if your job asks you, find me a fast solution to this traveling salesman problem, okay? You go back to your desk for a while, you try to figure it out, you fail, okay? What do you do when you go back and to talk to the boss, okay? One possibility is to tell the boss you failed because you were too dumb, okay? Maybe there's a fast algorithm out here, okay? I couldn't find it, okay? What's bad about that, okay? You tell the boss that, okay? The boss is obviously tempted to go and fire you and replace you with a smarter algorithm designer, right? Okay. What would be better in that case would be if you could go and stomp on the boss's door and say, you gave me a problem, I can prove to you absolutely that there is no fast algorithm for this problem, okay? You shouldn't ask it, you can't hope for it, okay? And that would involve a proof, rigorous proof, that there is no possible fast algorithm for it. And there's a problem with this, is that very, very few problems are there, where there are really convincing, absolute, cast iron proofs that there is no fast algorithm for it. What there is something, is what we're going to talk about for the next couple weeks, is something that is almost as good, okay? Which is a statement that, you're right, boss, I can't solve this problem, but nobody else in the world could solve it either, okay? You may want to fire me and hire Skiena, but Skiena can't do any more than I can, okay? You go to all the algorithm designers in the world, none of them can design a fast algorithm for this problem, okay? This is adequate for saving your job. Does everybody see that? You can convince the boss that nobody else can do it. It's almost as good as an absolute proof it can't be done, okay? But it is, and it turns out these can be done in a reasonable way, okay? These are actually, once you really get the hang of doing these things, it's often, to someone who's skilled in the art, okay, it's very easy to see often why a problem is NP-complete, okay? Meaning that no one else in the world can solve it. And this is a strong enough guarantee that for me, this is when I immediately say the problem, you give up on trying to find a fast algorithm on it. Because if no one else in the world can do it, I can tell you I can't do it either. Any questions about that? So that's sort of the basic motivation. And again, let's get back to sort of the theory here. Quite often this semester, we have come across problems for which I said there was no fast algorithm for it. One of them that's common is the traveling salesman problem. One of them was the bandwidth problem. You guys had that homework to find a bandwidth algorithm, a program for trying to find the optimal bandwidth of a graph. Okay? I said if anybody came up with too fast an algorithm, I would know it's wrong. Why is that? It's because this problem of finding the optimal bandwidth, no one else has a fast algorithm for it. And what's more is I have this kind of guarantee that no one else in the world could find such an algorithm. That would make me very suspicious of any fast program you guys came up with. Okay? Basically, there were a lot of problems that you come across in algorithm world where there is no algorithm that is really better than backtracking. Okay? I mean, we talked about bandwidth, we talked about traveling salesman. Were there any other NP-Complete problems I talked about this semester? Yeah?
I think we talked about 3-SAT for a little while, didn't you?
I will talk about 3-SAT later, so if I didn't talk about it, you didn't miss anything. But are there any other problems that come to mind? There are hundreds and hundreds of, I will even go back and say thousands and thousands of optimization problems people care about that turn to fall into this category where people couldn't find fast algorithms for it. And then in the 1970s, the early 1970s, they developed this theory. People, Stephen Cook and Richard Karp, sort of did different parts of this theory that basically gave the tools to show that all of these problems that people couldn't solve were really solve efficiently were really on some level the exact same problem. Okay, that's really what this whole machinery is about, is showing that all the hard problems in the world are on some deep level really the same thing. Okay, and so if you can prove your problem is one of these hard problems, your problem is hard. Any questions about that? Still sort of vague, vaporous stuff I'm talking about. But the next two slides are the entire idea of what we're going to do for the rest of the semester. And I'm going to show these two slides every lecture for the rest of the semester until you guys get the basic idea. Okay? This is we're going to try to, suppose I give you an algorithm, give you the following algorithm for solving the Bandersnatch problem. Okay? What is the Bandersnatch problem? It's the name of a problem. It doesn't matter what it is. Okay? Okay, well, right now it's just a problem. Okay? And it takes as input G. Maybe G is a graph. Maybe G is a gazillion length string. I don't know what G is. But it's an input. Okay? And suppose I gave you the following algorithm to solve the Bandersnatch problem. Okay? Which is take that input to the Bandersnatch G, translate it and reformat it. So you get a slightly different problem, input, Y, that is formatted as the input for the Bobilli problem. Okay, what is Bobilli? It's some kind of an algorithm problem. Maybe it's Bandersnatch, maybe it's shortest path, I don't know what it is. But it's a different algorithm problem. Okay? And let's say you've got a subroutine to solve the Bobilli problem. Once you have Y as input that's formatted appropriately for the Bobilli problem, you could call your Bobilli solver, okay, and get an answer back from it. Okay? So Bobilli of Y is the result of running the Bobilli subroutine on this translated input. Okay? The third part of this algorithm is simply to return this as the answer for that. Okay? Maybe I'll go to the pen here, because I'm getting a little bit here. That's right. Ka-chunk. Is this going to work? No. Let's see if I can get this here. Kabunk. So what is this algorithm going to do? Okay, let's try this in Kabunk. Okay? This algorithm is going to be for solving... Okay, looks like we're in trouble here. Okay, for solving this problem Bandersnatch, is going to do it by a three-phase thing. It translates the input, G, into a format Y. Okay? It then calls Bobilli on Y. You have a Bobilli solver. And it can compute, therefore, what the answer to Bobilli of Y is. Okay? And it returns, as Bandersnatch of G, the answer to Bobilli of Y. Okay? Now, under what condition is this algorithm correct? It may seem like a strange-looking algorithm. Under what condition is this algorithm correct? Yes?
Your subroutine for Bobilli is correct.
If Bobilli is correct, well, that's not the... First of all, if my algorithm for Bobilli is wrong, then all answers are off. That much should be clear. But Bobilli, just because it returns Bobilli, a Bobilli subroutine is correct, doesn't mean that it's going to give me the answer to Bandersnatch of G, right? Yeah. Saying G and Y must be isomorphic. Now, isomorphic is a big word, sort of meaning sort of the same. And in a way, I guess something's got to be the same about them. Okay? So I don't know if I'm going to quite use the word isomorphic for that. But it is clear that there's got to be something about this translation that is interesting. The important thing about this translation is that mobility of Y has to have the exact same answer as Bandersnatch of G. Does everybody see that if I am returning mobility of Y as the answer to this, if this is a correct subroutine, a correct algorithm for solving Bandersnatch, mobility of Y has to be the same as Bandersnatch of G, or else the algorithm is wrong. How many people see what I mean, see that that's necessary? How many people don't see that that's necessary? Okay, question. Why is it necessary? This is supposed to be a Bandersnatch algorithm, meaning that it will return the answer to Bandersnatch on any input, including this particular input G. Now, what the algorithm is doing under the hood is really returning the answer of mobility on a translated instance. Okay? So the only way that this can be a correct Bandersnatch algorithm is for every G if Bandersnatch of G was the same as mobility of Y. Does everybody see that? If I'm returning this is my answer, if my algorithm is correct, this answer had better be the same as my desired answer. Any questions about that? Okay? Fair enough. Now this kind of an algorithm may look weird, but it's actually an important type of an algorithm. It's something we call a reduction. Where is the hard part, in some sense, of this computation being done? The mobility subroutine is doing a lot of the heavy lifting here, right? We had a translation thing that just did the reformatting. But we have, in some sense, reduced the problem of solving Bandersnatch of G to this other problem, mobility. Okay? Any questions about that? So any time that we can translate our problem into another problem such that the answers are preserved, that's something we call a reduction. And this is an example of a reduction of two problems. Any questions? Okay. So what do we do with this? Hold on a second. I'd like to move on. Kabunk. Clear. Kabunk. Now, what good is this subroutine? Here is the punchline. This subroutine could do two different things for us. One thing it could do is, if we have a fast translation, if this translation, let's say, was fast, and mobility was a fast, okay, then this gives us a fast algorithm for Bandersnatch. Does everybody agree with that? It's a correct algorithm if mobility of Y is always the same as Bandersnatch of G. It is a fast algorithm if the translation, the conversion is fast, and mobility is fast. So this might give us a fast way to compute Bandersnatch. But the other thing that's interesting is, suppose I tell you that there is absolutely no possible way to compute Bandersnatch fast. I have a lower bound, I can tell you, for good reason, there is no fast way to solve Bandersnatch. What does this algorithm do? Okay? If there is no fast way to give you to solve Bandersnatch, and this is a way of solving Bandersnatch, what do we know about this algorithm? Yeah? We know that the whole algorithm can't be... We know that if there is no fast way to compute Bandersnatch, and this is a and this is an algorithm to compute Bandersnatch, we know this algorithm has to be slow. That much should be clear, right? And if it's slow, why is it going to be slow? If returning the same answer as that, well, returning an answer is just printing something out. That's not going to be slow. the translation might be a reason it was slow, but I'm actually described how to do the translation. Suppose the translation is not slow, and Bandersnatch has to be slow. The only thing that can be slow is mobility. Okay? So this algorithm is going to prove to be a way to prove to us that there is no fast way to solve mobility. Yes?
When you go from G to Y, you make Y really, really big.
Okay, so you're getting into a subtlety. You're saying, not big. The answer I would tell you is, if in the course of translating G into Y, you created something humongously big, how much time does it take to print out something humongously big? Humongous time. Does that make sense? The time it takes to print out something humongously big is linear in the size of the bigness, right? So the answer that he's getting at, which I don't really want us to talk about just yet, is that something different. This translation that we're doing here, among its other properties, had better not blow up the size of the problem very big, because if so, that translation wouldn't be fast. Okay? Any questions about it? So what is the argument here? If Bandersnatch sub G is absolutely positively hard, there's no fast way to do it. If you can show a way to translate the input of it, though, into G, such that the solution of mobility on the translated input, okay, would give us the answer we want, then that means that mobility also has to be slow. Okay? Because if there was a fast way to solve mobility, that would give us a fast way to solve Bandersnatch. And I'm telling you, there is no fast way to solve Bandersnatch. So this algorithm, with a guarantee that there is no fast way to solve Bandersnatch, is an argument that there is no fast way to solve mobility. Any questions about this? How many people sort of see the logic? Okay? Any questions? Okay? Normally, as algorithm designers, we are looking to solve Bandersnatch by translating it to a problem we can solve fast. For the purposes of proving hardness, what we're going to try to do is to take a problem we know is hard, figure out how to solve it using the problem we don't know about. If we can find a fast way to solve a problem we know is hard, using a problem we don't know about, we now know that that problem we didn't know about also has to be hard, where there can't be a fast way to do it because it would imply a fast way to do the other thing. Any questions about that? This is really the whole idea, okay? But it's really kind of an amazing thing, because it's going to give us a way to say that certain algorithms can't exist, okay? Which is kind of, again, it's a hard thing to think about. How do you do it? How do you prove unicorns don't exist, okay? It's very difficult, because you can, it always could be under this closet. Maybe I've looked everywhere else but this closet, okay? Okay, it's locked, okay? So, okay, the difference, though, is we're going to be able to prove that algorithms don't exist because of the result of what it would mean for the universe if it did exist. That's really what's happening here. Any questions about that before I move on? The whole argument again, okay? So let's think about what this algorithm does. I'm happy to say that again, and I'm going to say it again for every one of the next 3 classes, okay? We have an algorithm here that computes Bandersnatch, solves Bandersnatch, but it depends upon having a fast subroutine for a subroutine for this to solve this mobility problem. Now, if we have a fast mobility solver, this would mean a fast Bandersnatch solver, because what you have to do is you translate and you call this fast thing, right? But if instead we have a guaranteed certification that there is no fast way to solve Bandersnatch, and you're now showing me, wait, you're telling me there's no fast way to solve Bandersnatch. Here's a fast way to solve Bandersnatch if there was a good fast way for solving mobility. What I've really proven is together we have now proven there is no fast way to solve mobility. Because if there was a fast way for solving mobility, this would be a fast algorithm for Bandersnatch. And there is no fast algorithm for Bandersnatch. Therefore, as a consequence of there being no fast algorithm for Bandersnatch, there also can't be any fast algorithm for mobility. That is the reasoning that we're doing here. Any questions? Yes?
That's only if G maps to Y and one.
Well, I have to give you this translation so that this is depending upon, for this algorithm, the Bandersnatch algorithm to be correct, I've got to give you a translation of the input of G to the input Y so that the answers on the resulting problems are the same. Okay? If I can't give you that translation, I don't have an algorithm here, right? But that translation is something I can define and convince you it's correct. Okay? Any questions here? Again, that will be clearer once we start to do these kind of reductions. Any questions about philosophy? Okay, so let's talk a little bit more. Let's get into a couple of definitions here, and just to make sure we understand that we're talking about the same thing. First of all, this is going to be, when we talk about this, we're talking about problems. What do we mean by a problem? Let me see, this is not quite what I want. Let's say debunk. So what is a problem? When we as algorithmically talk about, okay, we've got this kind of a problem. What is a problem? A problem is a general algorithmic question. In my way of thinking, traveling salesman is a problem. Okay? I'm going to go through this carefully because there's going to be a distinction between three things we got to know the definition of. What is a problem? What is an instance? And what is a decision problem? These are the three things we're going to see. Okay? And none of them are really that complicated, but I want to make sure we get clear what's what. A problem in our definition is an algorithmic problem. A problem is the kind of thing in general that I will give you on a homework problem, on an exam, saying, here is something, give me a general algorithm for it. Something you can write a general algorithm for is a problem. It is specified by a question and an input format, okay? So a general problem is a question, okay? And it also has parameters for input and conditions describing what the desired output is. So what is the traveling salesman problem? The traveling salesman problem says the input is a graph, okay? And the output is what? It's a tour, okay, a permutation of the vertices, such that the sum of the edge weights encountered on that tour is minimized. Okay? That is what the traveling salesman problem is. Any questions about that? Okay? General problem. That's what we mean by a problem. We also have the notion of an instance. An instance is an input to a problem. Okay? What is an instance of the traveling salesman problem? Okay? An instance of a traveling salesman problem happens just to be a weighted graph. Any weighted graph, okay, is an instance, a potential instance of the traveling salesman problem. Okay? And we could describe that weighted graph in a couple of different ways. Okay? We could list the edges and vertices, and for every edge list the weight. We could use an adjacency matrix. We could use a couple of different representations. But an instance of a problem is the input format for that problem, is the actual input for a problem. A problem is a specification saying, give me input like this, and I will return output like that. An instance is the input data that matches that problem. Okay? Any questions about that? Do people see the distinction between an instance and a problem? One of the exam questions involved an instance. Like a couple of the exam questions, this particular exam, there was a mix of problems and instances. What were instances on the exam? Okay. What? Well, prime factorization It was a general problem. Okay, given a prime factorization, return all the factors, right? Yeah? Compute the minimum spanning tree of this, right? Here was a graph, and I said, give me the minimum spanning tree of this graph, right? Give me the edit distance on your macho, swap-powered edit distance of these particular strings, right? In one case, you're talking about particular instances. In other cases, you're talking about general problems which describe the format the instances have to have. Any questions about the difference between problems and instances? Any questions? No. Kabunk. Now, one thing that just to get at what he's getting at, he got at earlier, is that this is a minor technical point, and if you don't understand this, what I'm going to say now, it's not important. Okay, let me go back and say this much. It should be clear that there are differences in how you might represent the input of a problem. Okay? We might have an input, if we talked about our graph problem. We could use an adjacency matrix. We could use an edge list. Okay? He noticed something about what if my translation, my representation, the instance that I get after translating it, blew up to something humongous. Bad things happen if I come up with a humongous input instance. Okay? The key point which that we're going to be dealing with here is that if you talk about any reasonable problem, there are concise ways to describe an input and ridiculously large ways to describe an input. Okay? What would be a ridiculously large way to describe the number 100? 1 million. I'm going to try to write this thing down. Here is 1 million. Okay, am I right? And you're enjoying watching this because it's so slow, right? That's 100,000. That's a million, right? What would be a more concise way to write this down? First of all, yeah? 10 to the 6th, okay? 10 to the 6th. Okay, that's a much more concise way to represent it. What would be a much larger way to represent it? Yeah?
We could use an array of booleans, which all 1 million of them are equal.
Okay, one way that you could write it down like you're writing out check marks. 1, 2, 3, 4, 5, 6, 7, 8. Does everybody agree that this, if I keep going, will represent the number 1 million? But it's going to be a very inefficient way to represent it, right? We're going to be translating in this theory input instances to other input instances. That's what the conversion thing was, right? And this is an argument, basically, that when we convert them, we want to convert them to things that are about the same size. We don't ever want to do something like converting a number to something humongous, because that translation, when you actually write it down, is going to be very slow. Does everybody see that? On the other hand, a lot of different representations are going to be pretty much within polynomial size of each other. How many bits does this take to write down? A number of length n. How many bits will it take to write down a number in scientific notation? I've pretty much got to write down the base 10 logarithm here, right? Okay? How many digits are they going to be here? Okay? Basically the base 10 logarithmic number of digits, right? And for each one of these I have to write a number. Notice that this representation is pretty concise. I don't want to be held to this too much. This representation is also more concise, but not much more concise. Okay? This representation is slovenly bad. Okay? We're going to be talking in here about conversions of things. Basically, so long as when we translate things, the size does not change by an exponential factor. That's what's happening here. This is something going to be logarithmic in size. This is going to be linear in size. Okay? Then we didn't blow up the size and everything is fine. Any questions? If you don't understand this, hit the clear button for the last 2 minutes and don't worry about it for now. This is a subtlety we'll talk about later. Any questions? Okay? So don't worry about that. But the next thing is something to worry about. Okay? And this is a definition. We're not going to be, we want to be talking about why did we want to deal with this NP-completeness stuff in the first place? We wanted to talk about how hard it is to solve certain problems. We are going to deal in here with only a special class of problems. Problems for which the answer is either yes or no. Okay? A problem for which the answer can only be yes or no is called a decision problem. Okay? And for technical reasons, it's easier to deal with thinking about reductions of problems that are decision problems. Why is it easier to think about doing reductions on problems where the answers are only yes or no? Okay? Yeah?
Because it means that you don't have to worry about invertible functions when you're...
Okay, I don't know what that means. Okay, but I do know, okay, maybe, okay? But I'll tell you why, the gut reason why, yeah? Less cases to deal with. If Bandersnatch is a decision problem, what are the possible answers to Bandersnatch on any possible instance? It could be yes or no, right? If Bobilli is a decision problem, what are the possible answers for Bobilli? Yes or no. Our goal is to find a translation where the answers are the same on any input, right? In principle, it should be easier to make them the same if they are always only restricted to yes or no than if they can range on lots of values. This should make some intuitive sense here. Okay? We want to know that whenever Bandersnatch of G is yes, Bobilli of Y is yes. And whenever Bandersnatch of G is no, then Bobilli of Y is no. That's what it means to make the answers the same. And this is easier to reason about if the problems are always yes-no decision problems. How many people get that idea? How many people don't get that idea? Any questions about it? Okay? So from now on, we're only going to talk about decision problems. And this might make you a little queasy. Okay? You're saying, wait a second. You were busy talking to me about traveling salesmen a minute ago. I care about traveling salesmen. I care about bandwidth. Okay? Is that a true-false question? Is the bandwidth problem a true-false question? Well, it wasn't on your homework, right? You had to return an answer. So what am I going to be talking about that? It turns out that there is a natural way to convert most any optimization problem, most any optimization problem to a decision problem. Suppose we consider by typically saying, let's think about how do we make the traveling salesman problem a decision problem. Suppose we take as our input now a weighted graph and an integer k. Okay? And now we ask, does there exist a traveling salesman problem with cost less than k? Does everybody see that this is a decision problem? If I give you a graph and I give you a bound, and I say, is there a traveling salesman tour of this bound, of less than this? That is now a yes-no problem. Does everybody see that? In your bandwidth case, if I gave you a thing, said, here's a graph, is there a bandwidth solution of less than 15? That is a yes-no problem, right? And note that this yes-no problem captures what is really the interesting stuff about the traveling salesman problem or the bandwidth problem. Suppose I gave you a fast way to solve the traveling salesman decision problem, where for any graph and any bound, I told you, is there a solution of that bound? Okay, better or equal to that bound. Could you use that to find exactly what the size of the traveling salesman tour is? Okay, yeah?
We could just test the linear number of values between lower bound and upper bound, I think.
Well, we could use a linear search or we could use a binary search. Suppose I give you a graph where the heaviest weight on it was of weight M. I'm going to tell you a different letter. Let's say K. Can you give me an upper bound on the size of the optimal traveling salesman tour? If every edge was cost weight less than or equal to K. Okay? Yeah?
K times the number of edges.
K times the number of edges would be an upper bound, right? That's the upper bound of summing up all the edges in the graph. Can anyone give me a better lower upper bound? K times the number of vertices would be an even better upper bound. Does everybody see that? Because the tour is going to involve, you have to visit every vertex once, right? So now we know that the size of the optimal tour is between 0 and K times N, right? If we did a binary search, or if you want a linear search, but binary search would be a little bit faster, right? Saying, is there a solution of size Kn over 2 or better? We could use our decision problem, yes, no, to tell us that, right? If the answer was there is no tour of that size, then we would look, is there a tour that is 3/4 of the way up? Does everybody kind of see that? We have a range of values. The tour could be somewhere between 0 and Kn. I know this is terrible. If we go ask at the midpoint, is there a tour of at least this size? If there is, then the minimum tour has got to be of that somewhere in that range. If it isn't, the minimum tour has to be in this range. In one of these calls to the decision problem, we have reduced our uncertainty by half. By doing binary search, we would eventually find the optimal size of the traveling salesman tour. How many people see what I'm saying? Any questions about how many people don't see what I'm saying? This isn't that complicated so far. The point here is that the decision problems are as powerful for anything you and I really want to do as the full optimization problem. And they are easier to do this Bandersnatch Bobilli nonsense. So that's why we're going to limit attention to decision problems from now on. Any questions about that? So what's important to see here is if I can prove things about decision problems, I can prove things about the problems we really care about. And it's probably going to be a lot easier to do it about decision problems than the problems that I really care about. Any questions? Okay, good. Now, this Bandersnatch-Bobilli thing is what we call a reduction. And again, the idea of reducing a problem, one problem to another problem, is an honorable way to solve algorithm problems. By showing that, again, many problems we did, when we talked about sorting, we showed how to reduce many problems to sorting. How do you find out if an element is unique? Okay, if there's any duplicate pair in a set of n elements. Well, first sort it, and once it's sorted, then the problem is easy, right? How do we find the mode of an integer, of a set of integers? Well, first sort it, and once it is easy, then it is easy, okay? So we're going to use this idea of transforming one problem to another is something we have done, and is something that is a good idea for thinking about things. There's certain powerful sorting algorithm problems. Shortest path is a good example. Quite often when applications come in the door, I will try to say, well, if you think about your problem like this, it's really just a shortest path. And shortest path, Dijkstra knows how to solve it, right? So that's a standard algorithm technique. And it's an important thing. It's going to be what drives what we're doing here. But I want to make this clear, the importance of reductions. There's an old story about an engineer and a computer scientist who want some tea. Okay, they're sitting around. Sitting around. The engineer gets up, says, "I want some tea." He goes, reaches onto the shelf, pulls off the pot. Okay, washes the pot out, fills it with water, puts it on the stove, turns on the stove, gets boiling water. Okay, gets out some tea, puts it in a glass, pours the water into the tea, into the cup, okay, puts the pot back on, with the water on it, back on the stove, okay, and then starts to drink it. The computer scientist then says, hey, I also want some tea. So what does the computer scientist do? Takes the pot of still boiling water, pours it down the sink, okay, takes the pot, sticks it back on the shelf, and sits down. Why is that? He has reduced it to a solved problem. The engineer showed how to solve the problem of making tea from this case. Does everybody get that idea? Okay? That's what we as computer scientists are used to doing, and what we're going to be doing here. We're going to try to learn how to take our problem and reduce it to some other problem that we know about. Okay? Any questions about that? Okay? Again, you may not want to hang around a computer scientist if you're thirsty or something like that. That may be a side order here. But you get this idea about reducing things to things that we know about. Any questions? Okay, good. So now, let's talk. What I'd like to do to finish up the class, and we've got some time here, but I want to make sure we talk about this. This whole scheme of Bandersnatch and mobility, we now have started to flesh this out a little bit. Okay? Okay? We now know that Bandersnatch and mobility are both going to be yes-no problems. So that this translation idea, we know this translation of converting from one format to another had better not take too much time, had better not create something too big. But we know that we're going to be able to return the answer to this, because this is a yes-no problem and that's a yes-no problem. So we've made progress on it. The one thing that we haven't made progress on is what is Bandersnatch? Bandersnatch is a problem that we absolutely, positively know is going to be hard. Okay? And to make this whole thing work, we have to start from some problem that is absolutely, positively hard, is the mother of all hard problems. And what is the mother of all hard problems as far as we're concerned? It is a problem called satisfiability. So what I'd like to do is to explain what satisfiability is. Because when you first see it, it's a funny-looking problem. Okay? But once you get used to it, it's a very natural thing. Satisfiability is a logic problem. Okay? It is going to, logic means sort of like the kind of logic you did where you've got ands and ors and nots, okay? In particular, okay, what satisfiability is, the input of it, is a set of logical formula, okay? Or in particular, a set of Boolean variables, Boolean meaning things that can be said to be true or false, and a set of what they call clauses over these Boolean variables. The variables are v1 to vn. Okay? The inner clause is going to be an or clause. This comma, read the comma as being or. Okay? I know this is a pain in the neck. Or. Okay? And read this comma as being and. Okay, let me write that out there, and. Okay? And what is this saying? This particular input says we have two Boolean variables, v1 and v2, and a logic formula of the form v1 or not v2, and not v1 or v2. Okay? So each clause is an oring of a bunch of variables. I think you call that, is that a conjunction or a disjunction? Okay? Disjunction, I can't remember these things. Okay, it's an oring of a bunch of terms. Okay? And the outer commas are the anding of a bunch of terms. So let me go write this, since I can't write on my paper very well, on my board very well today. Let's try it up here. That's not going to work. Okay. Okay, hold on a second. Let's try. Okay, it shows what a weakling I am, I guess. There we go. Good. Okay, so what is this saying here? Suppose, let's say, we have in this equation, our equation was V1 or not V2. That's the way to read it. And, what was the other side? Not V1 or V2. The satisfiability problem says take a logic formula like this and see if there is any possible way to make it true. That's kind of what a lawyer does, right? The defendant has made various statements. He's trying to find some way to make them all true, okay? Suppose, let's say, is there any possible assignment of V1 and V2 such that this thing is true? Okay? Can anybody come up with a way to make this true? Okay? Yes.
You could set V1 equal to true and V2 equal to true.
Suppose we set that V1 was equal to true and V2 was equal to true. It'd be true or not true, right? What is true or not true going to be? True. Okay? This is what's not true going to be? False or true. False or true is equal to true. True and true is true. Does everybody see that? So the assignment, V1 is true and V2 is true, is a satisfying truth assignment to this. Is there any other satisfying truth assignment to it? Yes? Well, all of them. Let's try another one. What would be another one?
False, false.
Wait, first of all, I did this was true, not true, false. This was true.
True, true.
True, true is what I said. That was satisfying. You said true, false?
I said false, false.
False, false. False, false is also, this is good. False, false. This would be false or not false. Not false is true, right? This would be, so if it was false or true, that would be true. This would be not false would be true. True or anything is true. True and true is true. This is also going to be satisfying. But is everything going to satisfy? What if we add true, false? Okay? If we have true, false, this one looks fine. This is going to be doubly true, right? True or not false. True or true is true. This is going to be not true, which is false, or false. This is false. Does everybody see it? Two of the assignments satisfy. Two of the assignments don't. Okay? Any questions about that? What about another problem, though? Ka-chunk. Here is another problem where this one has three clauses to it. Maybe let me lower it just so you can see maybe the expression a little bit better. This one here has three clauses to it. Okay? Where it said, what we had before, V1, V2, V1 not V2, and not V1. Okay? The ands mean we have to make all three of those clauses simultaneously true. Is there any way to make all three of these clauses simultaneously true? Well, what would be the easiest way to deal with it? What do we know if all three clauses are going to be simultaneously true? What do we know about V1? V1's got to be false, or else there's no hope to save the last clause, right? So here we got V1 is going to have to be equal to false. Once V1 is false, what do we know that we have to do to save the second clause? It's got false or not V2. What does V2 have to be? False. And now if V1 and V2 have to be false, does everybody see that we're out of luck on the first clause? This clause has no, set of clauses has no way to make it true. So what is the satisfiability problem? The satisfiability problem states that I give you a set of clauses And I ask, is there a way to satisfy it? Some sets of formula you can satisfy, some formulas you can't. Okay? And the satisfiability problem, the mother of all hard problems, is trying to take the formula and tell it apart. Think about it a little bit. We'll talk more about this next class. Thanks for your attention. And if you did not pick up your exam, here they are.